of the Given I was pointed out that the traits are almost similar, not much different with the vanadium-2 case. On the other hand, relative rates involving chromium-2 and iron-2 reductions are significantly less than their rate of the water exchange reaction or water substitution reaction. So simply, from this data, one can say that the rate at which a coordinated ligand is given out from the reductant determines largely determines the rate of the inner sphere electron transfer reaction. And as far as rates of inner sphere electron transfers are concerned, they also depend upon rearrangement of the precursor complex and electron transfer. So, in the introductory part, related to inner sphere electron transfer reactions, you have seen that usually formation of the reactant pair is the very first step and it is reversible. Further, rate of such reactions are governed by the rearrangement and electron transfer step, and rate of an inner sphere electron transfer may depend upon the nature of the oxidant and reductant and bridging ligand. So from Taube's experiment, I have already concluded that reduction of hexamine cobalt 3 plus is with the hexachromium 2 plus under strict conditions occurs by outer sphere mechanism, while reaction is accelerated if amine ligand is replaced by chloride and it follows inner sphere mechanism. The enhancement is related to the symmetries of the reductant orbital and which electron is from which electron is given out and the accident orbital into which the electron is supplied. The simply nature of the orbitals involved on the accident and reductant metal centers, HOMO and LUMO orbitals, whether they are sigma type of orbital or pi type of orbital, and some data is given over here in this table. If it is sigma star type, then rate is lower, obviously in this range, and if it is sigma star pi type, or I've shown different systems over here based on chromium to cobalt to chromium to ruthenium 3, then vanadium to cobalt 2 and vanadium to ruthenium 2, and no data. All the all reactions occur by outer sphere mechanism. If this is the case, pi star type of orbital is involved on the HOMO and pi type of orbital is involved in the HOMO, then it is basically if it takes place where the outer sphere electron transfer mechanism. Otherwise, it takes if it is pi star, sigma star, pi star, the situation is like this, then the reaction takes place by inner sphere mechanism. And next thing is that, okay, in what way? You have seen that the inner sphere electron transfer process involves formation of a bridged species. And if bridged species brings the oxidant and reductant metal centers together, then its nature must influence the rate of the reaction. So, in this part, I would like to discuss briefly about in what way the nature of bridging ligand plays a role in determining the rate of the reaction. IM has basically pointed out that the role of bridging ligand in an inner sphere mechanism is dual. Firstly, it brings about two metal centers closer to each other, that is, it makes a thermodynamic contribution, and secondly, mediates the transfer of electrons, that is kinetic contribution. So the both thermodynamic and kinetic contributions are involved, and the thermodynamic contribution is related to the stability of the intermediate complex, whether it is uh, weakly, it is uh, stable, more stable or less stable, and kinetic factors such as oxidant reductant, reorganization, and matching of the donor and acceptor molecular orbital. So as far as bridging orbitals are concerned, both inorganic and organic ligands have been extensively utilized in the inner sphere electron transfer process. So we'll take some examples of both of these and try to have an idea about in what way they determine the rate of the reaction. At this stage, there is no question. While studying electron transfer reactions, one major problem is how to ascertain, how to affirm that the reaction is following an inner sphere or outer sphere nature. In this regard, a simple experiment has been basically devised, wherein a complex like this, I have really discussed about RX type of complexes. So C, cobalt 3 pentamine X halo bridge complex, complex halo complexes. When they are treated with hexachromium 2 under strict conditions, this type of reaction occurs. And in this particular case, you can see that if we change the X, we may observe a rapid, a swift increase or decrease in the rate of the reaction. Now, if we use azide or thiocyanate as a bridging ligand, we can have a situation like this, and we come out with a situation like this. The rate for outer sphere using azide ligand, ratio of rate of reaction of the outer sphere using azide ligand and outer sphere thiocyanate will close to 1, equal to almost equal to 1. While if we look about inner sphere, if the reaction is passing through inner sphere mechanism, then at a much greater than 1. Roughly X has been changed from azide to thiocyanate and it has been related, it has been basically concluded that using the simple ratio, one can have some idea about whether the reaction is following a outer sphere mechanism or inner sphere mechanism. And it is it may be related to the preferential formation of the intermediate in the inner sphere mechanism by one bridging ligand or other. And you already know that this azide forms a better, more stable intermediate as compared to thiocyanate. That's why actually this equation, this ratio has been observed. And it is shown over here, so I'm not going to discuss about it. This table simply K azide, K thiocyanate has been shown over here, and what is the progression of the reaction, whether it is following a outer sphere mechanism or inner sphere mechanism, has been concluded on the basis of this ratio. Now, an interesting piece arises. When thiocyanate is assumed as a ligand, and you know that thiocyanate acts as the emerantate ligand, and it can form a bond with the metal center through either end. Part through nitrogen end or through when NCS is S bound to an oxidant, as in this particular complex. CONH35SCN3. Nitrogen end of the ligand can be attacked by the reductant, and rate of this reaction is comparable to azide as the bridge. So this is basically the rate of the reaction for thiocyanate complex is close to 1.9 into 10 power 5 per mole per second, and for azide it is 3 into 10 power 5 per mole per second. The pent S bond bound thiocyanate can also be attacked by the reductant at sulfur atom directly bound to the reductant metal ion because it possesses two lone pairs of electrons. So when this attack takes place at the sulfur end, we